the people who have conservative ideas or right political ideas really should stop making arguments that are physics arguments that can be directly disproven by measurement and should get much more active in pushing free market solutions. If they did, I think that this problem could be solved in 20 years.
Hello and welcome to the Great Climate Debate Podcast. I'm Jeffrey DeSena. This week I have had the honor of interviewing two extremely smart gentlemen who have opposing views on the topic of climate change. If you've listened to Episode 8, you'll have heard the skeptic's view. Episode 9 is effectively a rebuttal. My guest today is Professor Scott Denning of Colorado State University. He received his master's and PhD in atmospheric sciences from CSU and has now been on the faculty for 20 years teaching courses in climate science, geology, and other topics related to atmospheric sciences. He has also been an avid science communicator and has been especially engaged with groups who are often more predisposed to reject the scientific community's perspective on climate change. He has generously given many hours of his time to answering my questions, but only one of those hours have I been able to get on the record. In the next episode, I will have to bring in a few of the topics we discussed in our pre-interview that I didn't have time to get into today. We discuss a range of issues related to climate change and his experience in climate change education, and he addresses a series of common misconceptions with practice skill that belies both their prevalence and his expertise. I bring you Professor Scott Denning.
So my name is Scott Denning. I'm a professor of atmospheric science at Colorado State University. When I was a little kid, I wanted to be an astronomer. When I got to college, they told me that they didn't have astronomy degrees, so I became a geology major. I worked for a little while in the oil industry after my undergrad, until basically the oil industry collapsed in the mid-1980s because the price of oil fell by 2/3. I worked for a while for the National Park Service doing water sampling up in Rocky Mountain National Park, and eventually found that I really loved research, so I went to graduate school in atmospheric science here at CSU. 5 years later, I had a PhD in atmospheric science. I went off to the University of California, Santa Barbara, for a couple of years in the mid-90s as an assistant professor, but was recruited to come back to CSU in 1998, and I've been here ever since on the faculty of the Department of Atmospheric Science. My research is primarily involved with the exchange of water, heat, energy, and carbon between the vegetated land surface and the atmosphere as part of the climate system. And I've maybe had about 25 graduate students throughout my career here. I've written over 100 papers in peer-reviewed literature, and I teach courses on climate and on hydrology and land-atmosphere interaction.
All right, very cool. Well, thank you for the very brief but informative synopsis. When we spoke last week, you talked a little bit how you really got interested in climate itself. How did you make that shift from geology over into climate science?
Well, of course, geology also is concerned with climate, but primarily paleoclimate, changes in climate over very long periods of time in the Earth's past. So I had this perspective about climate change over, hundreds of millions of years from my geology background. And then I started working with this study at CSU regarding transport of air pollution up from the Colorado Front Range up into the high mountains, Rocky Mountain National Park, which is west of Denver. And sort of learned quite a bit about precipitation and the wind and transport of stuff in the air. And that kind of led me to atmospheric science. CSU hosts the best atmospheric science department in the United States. And so I started taking courses over here, became much more interested in sort of not just paleoclimate, but how climate works as a system, as a process, as a machine, and then decided to go to graduate school in that area. So it was kind of a natural progression from the climates of the past that are revealed by the rocks to the climates of the present and the future that are determined by changes in the atmosphere.
If I remember correctly, one of the projects you were working on at CSU was funded by the National Science Foundation, correct?
Yeah. So I've more recently, starting in 2006, I became involved with a very large National Science Foundation center here at CSU that was developing a new way of representing clouds and rainfall in climate models. And my particular involvement, my role in the center, was to coordinate education and outreach to a broad range of audiences. So I did a whole lot of work with little kids. I supported the Little Shop of Physics here at CSU. We, during the 10 years that we were funded, actually visited over 500,000 kids in their classrooms here in Colorado and the region. We also developed a whole bunch of workshops on earth science and atmospheric science for high school science teachers. We had hundreds of them. We developed a big website that is visited still by more than 1 million people a month. So I started doing a lot of talks and lectures and workshops on climate change as part of that, and that's kind of how I became involved with communicating about climate change to popular audiences.
Mm-hmm. Well, I may well have been one of those kids that you all came and spoke to, but it was a long time ago. And was this program specifically focused on climate change or just physics and science in general?
No. Physics and science in general. And Little Shop of Physics is still out there. They are now supported primarily by CSU and by the College of Natural Sciences. But it isn't primarily a climate or weather-focused thing, although we do a lot of weather and climate in those programs too.
Very cool. And you mentioned a little bit about your research in climate modeling. I know that for a lot of people, the idea of trying to use these models to try to understand the climate systems leads to a lot of skepticism in whether or not we actually know what's going on, or these are just fictional futures created in computers. So can you speak to a little bit about how you build climate models and how you implement them?
Sure. There's sort of two questions there, and it might be worth parsing them separately. So on the one hand, there's a framing that you gave me that says people are skeptical of models in some sort of general way, and that's interesting. And then secondly, what is a climate model and how are they built? So I'll start with the last one, and then let's return to your framing about skepticism with regard to models in general. Climate models are basically weather models that we run for a really long time. So weather is determined by the motion of the air over the world. It picks up water from the oceans. It drops that water both on the oceans and on the land. The sun beats down in the tropics. That makes the air rise. The warmed air flows toward the poles. That makes jet streams and weather systems and all that kind of stuff. And these are classical physics. This is Newton's laws of motion and gravitation. It's the first law of thermodynamics, and adding heat to things warms them depending on their heat capacity, and warm air rises, and all that kind of stuff that you probably learned in a physics class somewhere along the line. But normally, those kinds of equations are used to forecast the weather. So, for example, when the weather changes dramatically from one day to the next, we know about those changes a few days ahead of time thanks to our ability to apply the laws of physics to the motions of the atmosphere. It's also the basis, for example, for how airplanes choose their routes from point A to point B to minimize their use of fuel and maximize their profits. So these kinds of quantitative calculations that are based on the laws of physics and applied to the atmosphere are very, very widely used in practical applications all the time. The trouble with weather forecasting is that you can't do it for more than about a week before the very small changes in the winds and so forth feed back on themselves to produce changes in the weather that you're not expecting. So everybody kind of knows that weather forecasts for tomorrow and the day after tomorrow are pretty good. Weather forecasts for a week from now are pretty iffy, and weather forecasts for 2 weeks from now are just out of the question. So the way that gets used in climate modeling is that the same processes happen on climate timescale, longer timescales, let's say over timescales of 10 years or 50 years or 100 years rather than 10 days. But it's no longer the details of those forecasts. So, for example, there's going to be some weather in the middle of December in 2032, but there's nobody who can tell you what that weather is going to be on a particular day 20 years from now. However, we know for sure that the statistics of the weather are not determined by the individual march of those storms, but rather by sort of the physical properties of the atmosphere and the Earth itself. So let me give you an example. The temperature in Colorado this time of year, end of November, might be very nice, might be warm and balmy, 60 degrees Fahrenheit or 15 Celsius, or it might be bitterly cold. It might be 10 degrees Fahrenheit, minus 10 or 15 degrees Celsius, and we really can't tell you what it's going to be. But I can tell you that the average temperature in November in Colorado is going to be somewhere around, 40 degrees Fahrenheit, 5 or 10 degrees Celsius. So the averages are behaving in a much more predictable way than the individual days. You know for sure that the summer is going to be warmer than the winter. The fact that you can't predict the weather 10 days out doesn't mean you can't predict the summer is going to be warmer than the winter. And that's because the statistics of the weather, that is the climate, is much more predictable than the weather itself. So climate models basically use the exact same equations as weather forecast models, but we allow them to run for many, many years, and we just ignore the day-to-day variations of that predicted weather and rather focus on the statistics of the predicted weather, the things like the changes in the averages. The averages are not changed because the individual weather events are changed. They're changed because something changed the boundary conditions of the system. So, for example, if I turned up the sun by a tiny amount, let's say by 0.1%, and the sun was a little bit brighter all the time, the world would get warmer. And that's quite predictable. That's a change in the boundary conditions of the planet as opposed to a change in the initial conditions of the weather. So climate models are the same as weather forecast models, but they are run for a longer period of time. Does that answer your question?
Yes, absolutely. And I think it answers a handful of other questions, but also brings up a bunch more. You didn't quite get to the point of being skeptical, but I kind of wanted to work my way to an event. But I first wanted to bring up something in the 2011 speech that I was just watching of yours at the Heartland Institute. The first thing you wanted to talk about was that arguing about the details is not worth our time. Well, it seemed that when we're talking about changes of a fraction of a degree over long periods of time, like that seems to be an important detail. Could you go into why the details in specific when we talk about climate science are not the most important part?
Well, for those of us who work in the field, of course, the details are everything. We spend all our time on the details. However, if you're just becoming interested in the field for the first time and learning about it, then I wouldn't start with something that it takes, a PhD and 10 years of research to find. I would start with the basics. And the basics are incredibly simple. Pretty much everybody understands this if they're reminded about it, is that when heat is added to something and subtracted from that, the difference between the heat in and the heat out is proportional to the change of heat of that object. So, for example, when you put a pot of water on the stove, you're putting heat into the bottom of the pot of water, and heat is being radiated by the pot out into the room, and heat is being released into the room by, say, boiling the water and turning it into steam. So the total change of heat in minus heat out is proportional to the change of heat in the water. That's the first law of thermodynamics. It's very fundamental. It is true that people have heard of this and people have experienced it in their daily lives, but many people have not thought about the implications of that with respect to the climate. Were you aware, for example, that precisely that same quantitative law of nature that controls the the temperature of the water in the pot on your stove is the same law of nature that makes day warmer than night, or summer warmer than winter, or Miami warmer than Minneapolis. So the fact that Miami is absolutely predictably warmer than Minneapolis, I mean, I can state with virtually 100% certainty that the average temperature in Miami next year will be warmer than the average temperature in Minneapolis for precisely the same reason that a pot of water will warm up on my stove. That's the basis of our understanding of global warming. It's not the details. You know, if you want to predict the temperature in Minneapolis next Tuesday, that's a much more complicated and difficult prediction to make. However, if your question is, how much warmer will the Earth be if we increase the amount of heat absorption by the planet, then you don't really need to worry about how the jet stream wiggles or what is the size of the raindrops falling in Iowa or some little detail like that. What I was trying to say is that the question of warming the planet when you add energy to it is a much, much simpler question than the details of how we forecast, you know, the wind speed in, you know, Paris on Thursday afternoon.
The speech that I was referring to was your 2011 presentation to the Heartland Institute, and I saw a little bit about your response afterward. Unfortunately, it was only the presentation that I've seen get on YouTube, but as I understood, there was a significant amount of time for Q&A afterward.
Sure.
What happened during that Q&A?
Well, I'm trying to remember. I mean, 2011 is a while ago, and I don't think I can give you a blow-by-blow of the whole thing. If it's the talk that I'm thinking it was, I had a number of typical questions or comments that one often hears from people who are hostile to the whole idea of climate change. So things like, well, hasn't climate changed before? And are you sure it's not the sun? And what about the emails that were hacked in 2009? And there's sort of a whole slew of these. You could almost Google, you know, climate skeptic talking points and get a pretty good prediction of what the questions and comments from an audience like the Heartland Institute would be. Let's try to sort of walk through that. My contention is that when heat is added to the Earth, it warms up. We can measure very precisely the absorption spectrum of CO2 gas and tell you very, very precisely and quantitatively how much heat is absorbed by how much CO2 and what the dependence is on water vapor and temperature and concentration and pressure, all kinds of stuff. So I can predict very accurately what the effect of CO2 on heat absorption is going to be, and I can estimate the rate of change of temperature that results in the Earth's atmosphere. When the question for that is, what about the sun? Well, the answer is the sun doesn't change the CO2 in the atmosphere, but certainly it's the same equations that relate the sun's change in temperature to the infrared radiation change in temperature. Absolutely, the sun changes the temperature, and for precisely the same reason, changing the infrared radiation changes the temperature. When the question is about hasn't the Earth's climate changed before, then the answer is yes, of course it has. And in fact, climate has always changed through geologic time. Every time there's more heat added to the Earth than removed from the Earth, the temperature goes up, and vice versa. Every time there's more heat going out than comes in, the Earth's cooled off. And we can even tell quite well from the geologic record how much heat in and out produces how much of a change in temperature. So we can get a pretty good idea of how sensitive the Earth's climate is to changes in the heat in and heat out. So then thirdly, with regard to the emails that were hacked in 2009, basically that's just a non-story. I mean, that's an interesting story, but has nothing to do with heat in and heat out. No matter what emails were stolen from what servers when, there's still some physical relationship between adding heat to the Earth and its change in temperature. It's still completely consistent with laboratory measurements, field measurements, measurements from airplanes, measurements from satellites, from the geologic record that shows us the sensitivity of the Earth's climate to heat being added and subtracted. So, I mean, that's kind of the flavor of the Q&A that happened after that talk. And really, frankly, almost any talk I give to audiences that are sort of predisposed to be hostile to the idea of climate change, I get pretty much the same set of questions every time.
Have you gotten any questions that you have found difficult to answer?
I guess what you're asking is, are there some sort of objections to mainline climate science that I find particularly persuasive? Is that what you mean?
Yes, much more precise way of asking that question.
All right, so let's see. I guess so. I think that the physical basis of our understanding of temperature and warming, when I say that, I mean everything from day versus night to summer versus winter to Miami versus Minneapolis to 21st century versus the 20th century. It's all the same physics, and I think it's incredibly well understood. So I don't find objections to that sort of basic physical story to be very credible at all. However, the next step in the story is, what are the impacts of massive global warming likely to be for our economy, for our society, for sea levels and human health and mass migration and things like that? I think those are basically social science questions that are not best asked of physicists like myself, but they're better asked of economists and demographers and sociologists and political scientists. Those questions, I think, are much less convincingly answered by academics. And I find when somebody says, well, it's not going to be that bad, even if, the seas rise 10 feet and it's, as warm as Florida in Washington, D.C., gosh, that's just not going to be that big of a deal. I'm skeptical about that point of view. I think I would need to see some evidence that that's not a big deal. But I don't feel competent to say that contention is just wrong on its face. If somebody tells me that adding heat to the Earth is not going to warm it up, that's just wrong, and it's easily demonstrated that that's wrong. But when somebody says, oh, we can have 5 degrees of global warming and not have economic collapse, I'm willing to listen to them. I think that's not a crazy thing to say. But of course, we should be very skeptical of claims like that, just like we should be skeptical of everything else. Then an even farther set of questions involves, what should we do about this problem? And people can reasonably argue about the relative merits of technological developments versus changes in the incentive structure of, carbon emissions in the economy versus international aid. There's all sorts of different policy responses that one might come up with. And again, this is just not physics, right? So I don't have any better idea of what ought to be done about climate change than you do or somebody else. Those are political questions. So I think that the physics of it is just really hard to wiggle out of. The social science impacts become more fuzzy, and I'm more than willing to listen to different points of view about that. And then on the political questions of what ought we to do about these problems, my gosh, that's really, everybody should have a voice in that. So I think the farther you get from the physics, the more difficult the questions become, and the more different points of view really need to be heard and to be weighed as we come up with answers for these things.
Mm-hmm. Absolutely, and that was one of your big admonishments of that Heartland Institute talk, was that the political right has been AWOL on this issue, and that they need to contribute their solutions as well, or else we probably aren't going to like what gets implemented.
It seems kind of silly to me for people whose main point is political, for them to be just asserting that the physics is bunk. Whereas, if they really want to argue physics, then get off the political high horse and let's get down and talk about physics, because that's something that can be tested. You want to make a claim that CO2 doesn't absorb heat? Well, then fine, let's go do some spectroscopy. You want to make a claim that heat doesn't warm things up? Then let's go to the lab and measure the change in temperature compared to the change in heat. Those are kind of non-starters. That's really not helping. But on the other hand, if you've got people from the political right who say, I think free market solutions are the answer, by all means, let's hear it. We've got a big problem on our hands, and we absolutely need contributions from across the political spectrum of ideas. If all of the ideas are coming from the political left, then they're not likely to be as effective as if we've got a broad spectrum of economic and political and sociological ideas in the marketplace of ideas and being debated and helping to inform our policy. I really think that we desperately need voices from the political right and the economic right with regard to how to solve these problems.
Mm-hmm. And you've been very good about reaching out to the right. You spoke at the Heartland Institute in 2011. You were invited back in 2012 to debate Professor Roy Spencer. But as far as I understand, you haven't been invited back, have you?
Yeah. Well, I did go back, I think it was in 2015, to their headquarters, which is now in a suburb outside of Chicago, where I did a televised debate with one of their scientists. More than anything, it's just a lack of schedule coordination. I mean, I'd be delighted to go back. I'd be happy to. It's not. I think that I don't need a specific invitation. They have these open conferences every summer, but I've had some conflicts and not been able to go back over and over. But yeah, I mean, I do a lot of events. I went and talked to to a big organization of Colorado ranchers and farmers down in the southern part of Colorado. I went to talk to the Western Stock Show. I don't remember the name of this big ranchers organization. Went to talk to the Republican Party of Grand Junction, Colorado. I've been to the state legislature 3 or 4 times. I try to do as many engagement opportunities as I can with people from the political center, the political right, because I think those people have, as I said, been kind of marginalized in this. I think we need to hear from those people on the sort of economic and social and political side. But what I hear mostly from them is criticisms of the physics, and I just don't think that's all that helpful. If you want to talk physics, let's get physicists to talk about it.
One small question that I did want to ask, because I recently spoke with someone who is very skeptical, and one of his big issues is that he worked for a long time on instruments and calibration, and he's seen how a lot of instruments can be poorly calibrated. And so when I sent him a link to some of the data that is widely used by climate scientists, he didn't see any references to how they were working their instrumentation. So how do you verify the data you're using or what data you're taking, and how do you trust the numbers that are coming out of your instruments?
All right. Well, I'm not primarily a field measurement guy, so it's kind of out of my area. But when we say climate instrumentation, I think we are probably referring to a very, very wide range of instrumentation that has changed a lot over the last 150 years. So, all the way back really to the invention of thermometers, measurements of pressure, measurements of water vapor, measurements of radiation. Some of these instruments are deployed at the surface of the Earth. For example, nowadays, a lot of the measurements that I use are from sonic anemometers. These are instruments which are essentially measuring the delay of an ultrasonic beep that is then received maybe 10 centimeters away in 3 different directions, and from that you can reconstruct the speed of sound. which is related to the temperature, and also the direction and speed of the wind in 3 dimensions. We do that 20 times a second. These instruments are calibrated, multi-step calibrations. You do it in the laboratory, you do it in the field, you have sort of reference instruments that you bring out. There's an awful lot to this field. It's really not my specialty. I just sort of said something about sonic anemometers, but there are hundreds, maybe thousands of different kinds of instruments involved. When we talk about spectroscopy, for example, that's the measurement of radiation at different wavelengths. And, of course, spectroscopy is the basis for all of astronomy. When we say stars are made of X, Y, and Z, or nebulas are made of X, Y, and Z, elements, that's based on spectroscopy. It starts in the laboratory. We do calibrations based on other measurements of the composition of gases, and then we run radiation through those gases and measure the absorption lines. That's how people measure your tailpipe emissions, for example. That's how they measure the composition of the atmosphere of Jupiter. Or, what this person is skeptical of is essentially all of modern empirical science, soup to nuts. Everything that's been measured for centuries is subject to these issues of calibration, of evaluation. There's a whole field of quality assurance and quality control in industry, which is sometimes abbreviated QA/QC. That is sort of maintained by a whole field of engineers. Within the United States, we have the National Bureau of Standards, NBS, which maintains absolute standards for many things. In Boulder, Colorado, there's a standard mole of carbon dioxide, literally measured by freezing CO2 out of air and then weighing it. That gets compared then to standard gases that are prepared in many different concentrations in reference cylinders. They're measured by spectroscopy in the laboratory. You send them out in the field. They come back after a year or so, and you measure them again. Boy, you're absolutely right. Almost everything in science, industry, the economy, regulations, laws, international trade, all comes down to being able to measure things to particular precisions and accuracy. And an enormous amount of work is done by thousands, maybe millions of people around the world all the time to maintain that sort of infrastructure of quality assurance and quality control of measurements. It's not just climate science.
Yeah, that kind of leads to another point that we talked about a little bit last week, was the idea of confirmation bias in the scientific community. Is that how does science actually correct itself when it seems that so many institutions or organizations have been set up to study anthropogenic climate change? It almost sounds like these research institutions have been created to confirm the hypothesis, not to try to disprove it, which is what the scientific method requires.
Science in general, not climate science in particular, but science in general underwent a revolution in the Renaissance and early modern periods. So think, say, from the year 1500 on, which was, in some ways, was the invention of skepticism. Prior to around 1500, Western civilization was built almost entirely on faith and confirmation bias. So pretty much the whole intellectual history of Western civilization before the scientific revolution trusted in revealed authority. So somebody a long time ago said something, and the best way to prove something was to find an ancient source, for example, from Aristotle or Plato or something like that, or the Bible, to confirm what people thought. It was only the invention of science, which, as I say, is really the invention of skepticism, that in some ways, it was the discovery of ignorance, elevating ignorance to a very high ideal in society. That's really science. So science is all about finding out new things which disprove old things, and using those disproofs, not proofs, to advance the state of knowledge. And I think it's easy to argue that the discovery of skepticism and the discovery of ignorance has propelled Western civilization to heights that have never before been seen in the history of the world. Pretty much all of the achievements of civilization in the last 500 years can be attributed to the elevation of skepticism and ignorance to a sort of scientific ideal. With regard to the way that works in self-correction in science, pretty much all of the advances in science have to do with testing ideas by experiment. So we try to write down very specific testable hypotheses and then design experiments that can, at least in principle, disprove those hypotheses. So, for example, we talked a little earlier about the hypothesis that energy is conserved, that the total amount of energy doesn't change, energy can be moved around. If I put more energy into something than I take out of it, then the amount in minus the amount out is equal to the change in the stored amount. That is a quantitative hypothesis that can be tested and has been tested over and over and over again through the history of science. So you literally can do it on your stove. You measure every joule of energy you put into that pot of water, every joule of energy that comes out of that pot of water, and the difference ought to be the change in the joules of energy in the water. Furthermore, the hypothesis that change in heat content is directly proportional to the change in temperature. This is 19th century thermodynamics. It can be tested. It has been tested. It's the foundation of science to test hypotheses like that. However, we don't just test the same old hypothesis over and over and over again because we haven't disproved it before. So, for example, I can hypothesize that when I drop a pencil, it's going to accelerate towards the center of the Earth, 9.81 meters per second squared due to the force of gravity. I can test that 1,000 times, and I will fail to falsify the hypothesis. It doesn't mean that it's prudent for me to test it 1,001 times or 10,001 times or 1,000,001 times. It's probably worth going on and testing a somewhat different hypothesis so that I can advance the science. Exactly the same thing is happening in climate science. So, for example, we are no longer getting much mileage out of testing the idea that adding heat to the Earth warms it up. It's failed to be falsified over and over and over and over again in the laboratory, in the field, in the outdoors, with airplanes, with balloons, with satellites. Nobody's going to get the Nobel Prize by proving that having a sunrise doesn't warm the world. However, they might get the Nobel Prize if they could somehow prove that, all of this is wrong. If somebody could actually prove that CO2 didn't absorb heat or heat didn't warm things up or that the world wasn't getting warmer, then absolutely they would be doing that, and they would be making hay. They would be publishing papers that got cited thousands and millions of times and wind up getting very prestigious awards and getting promoted and so forth. So I think that science self-corrects in a way that other forms of inquiry in human affairs do not self-correct. So, for example, you do not see self-correction like this in politics. You do not see self-correction like this in philosophy. But you do see self-correction like this in the institutional skepticism which we call science. I do not get papers published that say, yeah, me too, I get the same answer as everybody else. I get papers published and get rewarded scientifically by publishing papers that show that other people have been wrong. That's what makes science go.
And you brought up politics and philosophy, and this issue has become very wound up in politics on both sides. What do you think is driving that split of why this has become such a politicized issue?
The politics of what to do about climate change, as I think I said earlier, are not the science of what to do about climate change, right? The politics is, I am not a political scientist, but I do know some political scientists. Economics is the study of what people value, and political science is the science of how power is exercised in society. So when we talk about values and power, we are talking about people using the powers of persuasion, of institutions, eventually of armies, to get their way. And when you talk about political problems, absolutely, you are no longer talking about institutionalized skepticism. You're talking about people with an agenda who are doing everything they can to get their way, that are using power in society to achieve their desired ends. Why is that politicized, or how does that relate to climate change? I guess, this is not my field, but I guess that the reason that people with power want to interpret the results of climate science in ways to advance their agendas is because they have political power and they get to advance their agendas. I mean, it's like, asking why does the dog eat the cheese off the table? Because it can reach it, right? People whose job it is to manipulate other people and use political power to achieve their ends are going to do that no matter what. I think it's probably wise for all of us to remember that people will interpret current events in ways that will advance their agendas. It's certainly not unique to climate change. I mean, I think every aspect of politics has that. Think of any other issue that is in the realm of politics, the future of Social Security, or what the taxes ought to be, or what our policy ought to be towards Iran. All of those issues have people in power that are trying to manipulate other people to achieve ends that are in their interests. I think climate policy is no different from any other policy along those lines. However, I think it's quite a stretch to think that those political agendas matter a whit to the behavior of photons or molecules or pressure. It's an interesting contention. I have certainly heard people make statements like that, like the amount of global warming depends on my political opinion. I'm really skeptical of those kinds of contentions. Those are not well supported by evidence, those kinds of things.
When we talk about politics, and especially the communications around climate change, you mentioned forwarding such agendas, and I've definitely seen on both sides people either bending the facts or just highlighting things in such ways, and I see it from both sides, and you mentioned when we spoke last week that no one seems to be particularly hopeful about this, that conservatives say we can't do anything about it, and liberals say we can't do anything about it, so we're doomed. But you tend to take a different approach. You seem much more optimistic than most climate change communicators.
Thank you. I think that just sort of sticking to the facts, CO2 gas absorbs heat, and heat warms things up. So adding CO2 gas to the atmosphere will cause it to warm up. And this is actually pretty hard to argue with. I mean, like I said, it's based on direct measurements, and we've been making the measurements for 150 years. They've gotten better and better and better. They still say the same things they did 150 years ago. So the way out of that problem, if you want to get out of that problem, you have to stop setting carbon on fire, because burning carbon makes carbon dioxide. This is basic chemistry. Again, nobody really has produced any evidence whatsoever that that's not the case. So how do we stop setting carbon on fire? Well, there's sort of two parts of that. One is we have to be able to make money and live good lives without wasting energy. So we need energy efficiency. And the other basic strategy is to make energy that doesn't involve setting carbon on fire. So, lucky us, we have lots and lots of ways that we can make energy without setting carbon on fire. They include nuclear power, solar power, wind power, wave power, water power, all kinds of power. They probably include engineering different kinds of distribution grids and storage technologies. But like I said, those are in the details. We could argue about what the best ways to do that are, but that's kind of an engineering question. But the basic physics and chemistry points only to the need to stop setting carbon on fire. How we do that is entirely up to the political process. And I am quite sure that there are a range of different political options to do that. People on the left are going to probably favor large centralized investments in infrastructure, things like, massive power plants and new grids and a Green New Deal for the economy and big public works projects that'll put millions of people to work. People on the right might prefer structuring the incentives in the economy to reward entrepreneurs who invest in technology that produces energy without setting carbon on fire, or they might prefer some sorts of changes in the incentive structure that will increase energy efficiency. Whatever those political factions want to choose, as long as they're all working towards living good lives without setting carbon on fire, it's all good. From a science point of view, they all achieve the same end. What I fear is that only the left kinds of ideas are getting traction. That is, big centralized investments in huge infrastructure projects tend to get favored, and free market solutions aren't being favored because the people that we would hope would be promoting those solutions are too busy arguing that CO2 doesn't absorb heat or that heat doesn't warm things up. Those are just demonstrably false premises. They aren't political premises. They're physics premises that can be tested by experiment. The people who have conservative ideas or right political ideas really should stop making arguments that are physics arguments that can be directly disproven by measurement and should get much more active in pushing free market solutions. If they did, I think that this problem could be solved in 20 years. I mean, it's a big problem, but this is something that the left politics doesn't really want to hear, is that the solutions to climate change involve global expenditures sort of on par with what it costs to build the internet or what it costs to put PCs on every desk in every office in the world, or to invent and deploy global phones, mobile phones globally. So these are big things. For example, the cost of the internet, the total cost of the internet since 1990, absolutely dwarfs government programs like Social Security, right, or the U.S. military. Obviously, the U.S. military is a big organization, costs a lot of money, but it's peanuts compared to the internet. So yeah, solving climate change involves expenditures more like the internet than like Social Security or defense, but those costs are borne by everyone and are essentially providing the whole world economy. I mean, what would the world economy look like today if all of the money that was spent on the internet was not spent? Well, I'll tell you, there'd be a whole lot less jobs in telecommunications, right? What would the job outlook be like in fiber optic cables if it weren't for the internet? Just the same way, I think solving climate change is going to involve massive investment in the private sector. It's not going to be mostly the government. It's going to be businesses that are going to spend that money. Pretty much all the job growth over the next 20, 30 years is going to be involved in deploying those new infrastructure technologies. So I don't see it as being an insolvable problem. I think this is totally within our capacity as a civilization to do, just like the internet was within our capacity to do. If somebody had just toted up the costs of the internet back in 1990 and said, oh my God, we can't afford that, Well, they would have been wrong because we did afford that, and it didn't make us go broke. Arguably, the internet has been a huge success. Lots of people use it. There's lots of jobs. There's lots of economic growth, and clean energy be just the same way.
Well, all right. I love that perspective, and I will try to embrace it and spread it myself, but that hour slipped away far too quickly.
All right. Well, it's fun to talk with you.
Yeah, it's been an absolute pleasure, and thank you so much for the time you've already given me, and I hope we can stay in touch, and hopefully you keep spreading good information and good skepticism.
All right. You too.
If you enjoyed this conversation, please subscribe on iTunes, Stitcher, YouTube, or wherever you prefer to get your podcasts, and please share with your friends on social media or maybe even in a real-life conversation. You can find links to some of the things we discussed in the podcast descriptions on YouTube, SoundCloud, and iTunes. This has been the Great Climate Debate Podcast. I'm Jeffrey DeSena. Thank you for listening.